I present our work Continual Learning in Open Vocabulary Classification with Complementary Memory Systems. This work is accepted by Transactions on Machine Learning Research 2024. Imagine a bird classification app that can predict any bird species and is able to continually improve from users' feedback. If I'm using the app and I took a photo and I notice that the app makes a mistake, I would want to correct that mistake and have the system update very quickly. So next time when we upload an image of the same bird, the app can make correct predictions. And also, the system is able to maintain its ability for species that it already knows well. Similar to this app, our goal for this work is to create a classification system that obtains efficient training, flexible inference, and continual improvements. To create such a system, we start from CLIP because it supports open vocabulary classification by comparing the similarity between image embeddings and text embeddings and then choosing the label with the maximum similarity. Therefore, it is able to perform flexible inference well. Comparatively, the inference of traditional classification models is only constrained to the training labels. Let us examine how previous works perform in these goals. A clear message here is that not a single method that performs well in all goals, even for ZSCL, which is a recent work aiming to improve the continual learning ability of CLIP models. So, what is the reason for this? The underlying reason can be twofold. First, deep models like CLIP typically learn from large datasets to achieve flexible inference capabilities. However, updates from a small subset of samples can be disruptive to other tasks. Let's consider an illustration. We start from a model trained on a large dataset. When a new training sample is added, the model shifts to incorporate this new example. But this change may cause the model to lose performance on original tasks. As a summary, dense models typically learn weights through optimization, and their performance is often impacted by interference between samples. However, they generally generalize well. On the other hand, we can consider instance-based methods. Instead of learning weights, these models lazily store training samples and use them as references. During inference, they compute distances between the tested sample and all stored samples. Predictions are then made based on the labels of similar samples. Due to their nature, instance-based methods are not troubled by interference, allowing them to continually improve with new data. However, they cannot generalize to novel labels as effectively as dense models. Our idea for this work is to combine these two models together to achieve continual improvements and flexible inference. To add the instance-based system to CLIP models, we create an example set which stores the image embeddings from the training images. Also, we will need to store their labels. Example set alone cannot make predictions. Therefore, we create example models which learn from the example set and make predictions according to the inference sample. Naively, according to the literature, KN is the simplest instance-based method. Essentially, it works by comparing the image embedding to all atoms in the example set, and then select the most similar K atoms. Then the classification result is made by majority voting. The advantage of KN is that it does not require any training, and its inference speed can be made super fast by using advanced indexing libraries such as FAST. However, the downside is its performance is usually not great. Another easy example model is linear probe. Basically, whenever there's a new sample added to the example set, we retrain a linear classifier on all available data. The performance of this approach is good, but it can be slow since the learning complexity is O(n), where n refers to the size of the example set. Assuming there are already millions of data points in the example set, the time needed to incorporate a new sample can be very large. By combining the advantages of KN and linear probe, we propose tree probe. which hierarchically stores data in the leaf nodes of a tree. Whenever a new sample is added to a leaf node, we will retrain the classifier attached to that node by using all samples stored in that node. Each leaf node has a node capacity, which indicates the maximum number of samples that node can store. Next, we will show how the tree is built. At the beginning, we create a root node. New samples are stored to the root node until its capacity is reached. When producing two children, we perform k-means clustering with two clusters to distribute the data to the corresponding leaf nodes. Each leaf node also maintains a classifier so that whenever a new sample is stored to that node, the classifier is retrained on all samples stored in that node. With more data, now the blue leaf node's capacity is reached. Similarly, we perform k-means clustering, and this blue node produces two children and turns into a father node. Now, we have two systems, the CLIP image encoder, which is good for general cases, and their example model, which excels at learned tasks. We will need to merge their results together to take advantages of both models. We think of merging as weighting their outputs. Assuming the weight for the example model is alpha, then the weight for the CLIP model is 1 minus alpha. Naively, alpha can be set to 0.5, which assumes equal importance of both models for any cases. This is not intuitively appropriate because both models have their own expertise. To address this issue, we proposed a weighting method called Hoiem. The main idea is to assign more weight to the example model for seen labels and assign more weight to CLIP for unseen labels. However, the challenge is that at test time, we don't know whether the label of the inference sample is seen or unseen. We will need a way to estimate the likelihood of a sample belonging to seen or unseen classes. How can we solve this problem? Well, we can think in this way. We know that CLIP underperforms the example model only for seen classes. Therefore, we can sum up CLIP's probabilities for all seen classes as the confidence measure. If the sum is small, it means that CLIP's confidence for the sample belonging to seen labels is low. As a result, we should trust CLIP's prediction more. If the sum is large, it means that it is highly likely that the sample belongs to one of the seen labels. Therefore, we should rely more on the example model for the final prediction. Here is the equation of how to calculate the weighting. And we also create a demonstration of how to calculate Hoiem. Assuming the candidate labels are cat, dog, bird, fish, and seen classes are cat and dog, we have computed CLIP's probability for the input sample as the following chart. Then the weighting is simply summing over the probabilities for cat and dog. Now we concluded our method, and I will introduce the experimental settings in more details. We define task as a mapping between images and a set of labels. Target tasks are standard classification datasets such as CIFAR 100, Oxford Pass, etc. We use the training data from target tasks to train our model, therefore their labels are seen labels. Zero-shot tasks refer to the datasets where we only use for evaluation. Models do not see their training data, so their labels are not seen during training. We evaluate our method under the task incremental learning scenario, where we treat each target task as an individual stage and train the model sequentially on these stages. Performance is evaluated after each stage as the average accuracy across all target tasks. Class incremental scenario splits an individual task into several stages, and the split is driven by labels, so each split has long overlapping classes with other stages. Model is trained sequentially on these splits for individual target task. We average the accuracy on each target task after each stage as the performance for the model in that stage. Different from class incremental, the split for data incremental is driven by samples rather than labels. So there are overlapping classes across different splits. We also build evaluation scenarios to evaluate models' ability to perform flexible inference. The key idea is to create tasks that are composed of random samples from both the target and zero-shot tasks and random candidate labels from both tasks. Among these scenarios we created, zero-shot helps easily pinpoint whether the model experiences forgetting as we start from clip. Here are the results we performed under the task incremental learning scenario, where we show the benefits of dual system design and our aim weighting method. Of these three methods I circled, clip zero-shot and NIM-probe are single models. Clip keeps constant accuracy throughout, whereas NIM-probe can improve when seeing more data and eventually surpasses clip at the final three stages. However, clip plus NIM-probe with the average weighting is generally better than NIM-probe, showing the advantage of dual systems. If we change the weighting to our aim method, we can notice a dramatic improvement, and this method is the best across every stage. We also perform comparison under data and class incremental learning scenarios, and the same conclusion holds for these two cases as well. The results on flexible inference are important, especially the zero-shot evaluation can be an indicator of forgetting by comparing to clip zero-shot. From this plot, we can see that our final model in the purple ball under the zero-shot evaluation has a very similar performance to clip zero-shot in blue, showing that our full model does not have a forgetting issue. In general, our method has the best flexible inference ability. This figure illustrates the time needed to add one new example for different example models. The x-axis shows the number of samples that are already inside the example set. The orange line shows the results from linear probe. It clearly shows that linear probe adheres to linear learning complexity as the number of instances in the example set increases. Regarding our proposed tree probe with different node capacities, a clear message is that when the node capacity of the root node is not reached, tree probe only has one single classifier. Therefore, it shows identical learning complexity as the linear probe. After reaching node capacity, tree probe exhibits constant learning complexity. The tree probe 100K and 50K achieves similar performance to linear probe, but with 6 times and 25 times improvement in learning speed. We also compared to previous methods under the benchmark proposed in ZSL. Our method achieves the best performance under every metric. To summarize, we proposed a dual system framework for open vocabulary continual learning, proven to excel at flexible inference. We also proposed tree probe, an exemplar-based method with competitive results as linear probe but with smaller learning complexity. We also propose aim weighting that effectively combines the results from example model and zero-shot model, offering decent performance under various testing scenarios. Thanks for sparing time with our paper. If you are interested, please feel free to scan either the code or the paper to learn more.